My name is Boris from Amdocs. I'm going to speak about a very interesting topic to balancing between latency and accuracy in NWDAF. So in general, NWDAF is network data analytics function. This enables analytical capabilities on top of collection of data from all over the 5G network. The second term is network function, which is a functional building blocks within a network. It is well defined, the inputs and the outputs, and its functional behavior. So I'm going to go through an example, which is NWDAF NF Load prediction. We need to estimate, predict different metrics, different load metrics like CPU, memory, and disk on top of this network, different types of network functions. We have as an input to our problem is about 30,000 time series in 15 minutes granularity, and the task is to predict 10 points ahead to the future. Again, every point is 15 minutes aggregation. So, okay. So our problem is to generate a good quality model in a low latency and with low cost computing power. So this is something that comes from a lot of our customers to create some solutions that can be used in low cost computer power, because customers don't want to spend a lot of money on expensive hardware and to the cloud or some premise. We can see here some very nice example of our model. We got is an input history length of 60 points, and the orange points is the actual one. The blue one is a predicted. We see that the model predicted very well. Also very nice to see is this orange dot above that the model also predicted very well. Okay, so our agenda is we are going to define our success criteria. I'm going to go through a number of practical tips and tricks that we have used to be able to solve this problem. And finally, I will show you our architecture for ML trade-off selector between accuracy and latency. So before we defined ourselves by business requirements, three rules. Three criteria. So one of them is to be able to predict, to generate a model with a prediction metric SMAPE with less than 10%. SMAPE is a very known used metric for time series, symmetric mean absolute percentage error. The latency should be less than 15 minutes for all our time series data. And again, the solution should be work on top of low cost computing power. So this is the criteria. Now I'm going to go through 4 practical tips and tricks that I have used. Vectorization and low-level framework. I'm going to speak about every each one in next slides. Polarization, just-in-time compilation, and model tuning. So the first one, vectorization low-level frameworks. As most of you know, Python is an interpreted language, which means that it executes the code line by line and converts these lines to machine code, and it is relatively slow versus compiled language like C, which is much faster. So the first step is trying to use low-level frameworks as NumPy. The core of NumPy is well-optimized C code, and most of the code is pre-compiled, which means it runs a lot much faster than native Python code. Also try to use vectorization instead of loops. I generated here a very simple example just to show the differences. We can see here on the left, I have simulated 2 vectors A and B. I just made a simple multiply A by B. So in the middle, we can see here a regular for loop. that took about 4,000 milliseconds. And then exactly the same one with NumPy is YA multiplied by B. It took less than 40 milliseconds, 100 times faster. So it just give you a taste these huge differences by using this kind of low-level frameworks. The second one is parallelization. In Python, we have a variety number of available Python packages like joblib, Dask, Ray, pandas parallel to be able to parallel pandas. It is very important. We can see here, for example, the below screenshot from HTOP from 80 cores server that it well optimized. I see a lot of people pre-process data. They do not usually parallelize their codes, so just work in one core. And there, in many cases, are many more than one. So it also saves a lot of time. Another very important package that we got familiar with during this project is Numba, just-in-time compiler. It's a very interesting package because it takes Python, a NumPy code, and translate into machine code. For example, if I have some group by apply code that I'm calling to some function millions of times, so on the first time it will compile it, put it in a cache, and the rest of the calls will be go through this pre-compiled function code, which makes the run much faster. We can see here on the example on the right is that part of our project we should do forward field and backfill to handle missing values. So at the beginning, we have used the built-in pandas function, but it wasn't enough. We could not finish our cycle of 15 minutes in this code. So we rewrite this functionality using Numba. And you can see it saved us about 25% of time. It was 25% faster just writing the same functionality using Numba. The last trick, it's a model tuning. So try to use more light frameworks, and you can tune it initialization processes. For example, you can just random some the parameters of this model, for example, trend, seasonality, and the level what you have used, or try to hypertune them, which will take more time. So if you just random these values in the model, it will run much faster. Sure, it will come with a cost in performance. So by combining all these tricks, we reduce time more than 2 minutes or save, which is a lot in our 50 minutes time span limitation. So it actually works. Now I would like to introduce to you our architecture of ML trade-off between the accuracy and latency. So again, it's always a trade-off. So we can see here on the left the input to our ML trade-off selector set of time series. We have this 3000 time series. We have another table with the metadata that the admin can set up or config this metadata per each time series. Each time series will go through another some flow. We have 4 different flows with this kind of trade-off between accuracy and latency. We have the first one is the fastest one, so we have some requirements to finish the full cycle of 30,000 time series in less than 1 minute. So we less care about the accuracy, we much more care about the latency. So we apply seasonal naive model, which means we just take, if we in daily data I would like to predict the next Tuesday, so we'll just take the last Tuesday that we have in our history. It's very fast solution. not so accurate, but latency is very fast. The second one, we have intermediate flow. We would like to increase the accuracy and still be relatively fast. We have here 15-minute cycle, so we must finish all the time series in this time. So we are using hot winter model. It's with grid search optimizer, so we optimize this starting parameters, trend, seasonality, and the level, and we also able to generate multiple feature simulation to the prediction in order to generate prediction interval, not just the points of the predicted point, also the prediction interval is something we didn't do in the fastest flow. Another optimization in this part, that if we identify automatically some time series that are relative static one, so we automatically just, instead of training in predicting results winter, we are using a naive model. So if this time series static one, so we'll just predict the previous values to the future. This third one is accuracy flow, 30-minute cycle. So we less care about the latency, and they would like to increase our accuracy in the models. So we're applying ensemble between multiple univariate models, such as Hot Winter, Theta model, the one that won in the M3 competition, known time series competition, Prophet, NeuroProphet, and also I'll be able to add prediction intervals. And the last one, the last flow, is a most accurate one. For example, we have a weekly cycle, so we much less care about the latency. We would like to have the most accurate model. So all this time series will go through this flow, will generate the most accurate result. And this is based on the deep learning approaches. I wanted to show also how we use generating the prediction interval. So with Alt Winters, this have some built-in stats model configuration, so we can in a very quick way generate multiple future simulations, and then take the 50th percentiles and the 95 one, and then we have some prediction interval for each horizon length. So we have SOS 10 steps. So we do the same calculation per each, and in such way we have a very quick way. Multiple we have a generated prediction interval. So without retraining the model again and again, it's based on the first model that we trained. We also winter model. Okay, so this is the last one. So we have defined our criteria, so that our model must be at least, the ASMAP must be at least 10% and less. All the cycle should be finished during less than 50 minutes. And the requirement is to produce a solution on top of low cost computation power. We go through the practical tips and tricks that we have used in our code in order able to improve our latency. And at the end, I showed you our architecture that is being used to trade off between different accuracy and latency per each time series in our data. That's it in general. So if anyone have question, this is the time.
Thank you, Boris. It was very interesting, and I would like to present you with 2 questions. One of them is about load metrics for the network functions. Why you want to predict them? What is the reason for predicting them? You can elaborate some more. And the second question, well, let's start with the first one, and then I'll.
So the first one is what again? Why we want to predict to generate a good
Load
quality,
metrics for the network functions.
because it is important to estimate this, to generate a good model to be able to catch these changes. If we have some high CPU, high RAM, so it's very important to identify this to be able to ensure high quality of service to our customers, because these network functions today are being installed on the physical hardware or virtual one. So to be able to keep good quality of service to our customer, we must identify this ahead, applying this time series prediction model, and then the network can react accordingly to this, keep high quality service. That's it.
Okay, and another, thank you. Another question is, do the short latency models use the results of the longer latency models?
Again, what?
The question is about the short latency models. Are they using the results of the longer latency models?
No.
Do the different models are interacting, or it's separate?
No. It's a different. I see. No, it's a different. It means the 4 pipelines that I showed on the last slide. No, it is every pipeline is a separate one. Every time series has using the metadata is route to another one. So no, it's trained and separately. There's no connection between the pipelines. They're not talking each with other.